Hello everyone, welcome to this lecture on Newton's interpolating polynomial. In the previous lecture, we studied the Lagrange form of interpolating polynomial. Today we will learn Newton's form, which is computationally more efficient form. First, we discuss the idea behind Newton's form. Suppose we are given n plus 1 distinct nodes x0 to xn. These nodes belong to some interval I, and a function f of x is given, which is continuous real valued function defined on interval I. Our goal is to construct an interpolating polynomial px of degree n for n plus 1 distinct nodes such that p of xi equal to f of xi for I equal to 0 to n. Key idea of Newton's form is that instead of writing px in powers of x, Newton suggested to write the interpolating polynomial in a product form, this form. In this form, the first term is constant, second term contains one factor x minus x naught, third term contains product of two factors x minus x naught, x minus x1. Next term contains product of three factors x minus x naught, x minus x1, x minus x2. So each new term adds one new factor corresponding to the next node. This form is called Newton's form of interpolating polynomial. Now we apply interpolating conditions. First interpolating condition is px naught equal to f of x naught. Okay, from here. So substitute x equal to x naught in px. See, all terms except a naught contain the factor x minus x naught. All terms. So all these terms will be 0 when we put x equal to x naught. So we get here p of x naught equal to a naught. This implies a naught equal to f of x naught. Now we apply second interpolating condition, p of x1 equal to f of x1. So we substitute x equal to x1 here. So in this case, terms containing x minus x1 factor will be 0. Okay, so from here p of x1 will be a naught plus a1 x1 minus x naught, and this fx1 we are writing. So already we have evaluated a naught equal to f of x naught. So now we solve this equation for a1. So we get a1 equal to f of x1 minus f of x naught divided by x1 minus x naught. So this quantity is called first divided difference. In a similar way, we can apply other interpolating conditions and substitute x equal to x2, x equal to x3 in px to obtain the other coefficients. Other coefficients means a2, a3 up to an. Now we understand the most important concept behind Newton's interpolating polynomial, that is divided difference. Suppose we are given n plus 1 distinct nodes x0 to xn. These nodes belong to some interval I with the corresponding function values f of x0, f of x1 up to f of xn. So for I equal to 0 to n minus 1. Okay, so here we have n plus 1 distinct nodes. I we consider from 0 to n minus 1. The first order divided difference is defined as, we denote first order divided difference by this expression. You can see here f of large bracket xi comma xi plus 1. It is equal to f of xi plus 1 minus f of xi divided by xi minus xi plus 1 minus xi. See, first divided difference simply the slope of the straight line joining the points xi f of xi and xi plus 1 f of xi plus 1. So this is the slope of this straight line. Okay. Uh, now second order divided difference. The second order divided difference is defined as f of xi plus 1, first order divide difference for nodes xi plus 1, xi plus 2 minus first order divide difference for the nodes xi and xi plus 1. So you can see here second order divided difference is defined in terms of first order divided differences. Okay, so while the first divided difference measures the slope of the straight line, second divided difference measures the change in the slope. So in general, we can define the nth order divided difference, which is defined by this expression. You can see here. Uh, Here first we find the divided difference for these nodes x1 to xn. Okay, minus divided difference for nodes x0 to xn minus 1 divided by xn minus x0. Okay, see here each divided difference, each higher order divided difference is computed, is defined using the previous order divided differences. To organize calculations, we use divided difference table. This is the divided difference table for four distinct nodes. In the first column, we simply write nodes. In second column, we write corresponding function values. Now we compute the first order divided difference. So these three are the first order divided differences. So here, first one, f of x0, comma x1, it is calculated as f of x1 minus f of x0 divided by x1 minus x0. Other divided difference, first order divided difference, we can calculate as f of x2 minus f of x1 divided by x2 minus x1. Similarly, f of x2 comma x3, we calculate f of x3 minus f of x2 divided by x3 minus x2. So after the first order divided differences, we compute the second order divided differences. These are the second order divided differences. So second order divided difference for nodes x0, comma x1, comma x2, it is calculated as this first order divided difference minus this first order divided difference divided by x2 minus x0. Similarly, f of x1 comma x2 comma x3 means second order divided difference for these three nodes is calculated as first order divided difference for nodes x2 x3 minus first order divided difference for x1 x2 divided by x3 minus x1. Now observe the pattern. Each value is computed from the two values directly to its left. Okay, this value is calculated from these two values. This value is calculated from these two values. This value is calculated from these two values. Okay, finally we compute the higher order divided difference, which is this one. So it is calculated as second order divided difference for nodes x1, x2, x3 minus second order divided difference for x0, x1, x2 divided by x3 minus x0. See, this table forms a triangular structure. Here, most important point is that all first entries, all first entries, all first entries of each column are the coefficients of Newton's interpolating polynomial. Now we discuss a final statement of Newton's polynomial. Given n plus 1 distinct nodes x0 to xn and corresponding function values fx0 to fxn, there exists a unique polynomial. Here unique word is important. Unique polynomial that we denote by Pnx of degree less than or equal to n, written as Pnx equal to a naught plus a1 x minus x naught plus a2 x minus x naught in x minus x1 plus and so on. So in product form we are writing this polynomial satisfies the conditions Pnxi equal to f of xi for I equal to 0 to n. These conditions are called interpolating conditions, and here the coefficients a0, a1, a2 and so on an are divided differences as we have already discussed. So a0 will be zeroth order divided difference, that is f of x naught. A1 is the first order divided difference for nodes x naught and x1. A2 is the second order divided difference for nodes x0, x1, and x2. And in general, we can write an is the nth order divided difference. Now we discuss Newton's form of linear interpolating polynomial that is obtained for n equal to 1. Here n equal to 1 means we have two distinct nodes x0 and x1 and corresponding function values f of x0 and f of x1. For two nodes or for n equal to 1, Newton's polynomial will be of degree 1, which is defined as p1x equal to f of x0 plus first order divided difference x minus x0. Now substitute the expression for first order divided difference, that is f of x1 minus f of x0 divided by x1 minus x0. We get p1x equal to this expression. If you look at the diagram, p1x is simply the straight line joining the 2 points x0 fx0 and x1 fx1. So for n equal to 1, Newton's interpolating polynomial is a linear polynomial of degree 1. Now we discuss quadratic interpolating polynomial. So for n equal to 2 means we are having three distinct nodes x0, x1 and x2 and corresponding function values fx0, f of x1 and f of x2. For three nodes means for n equal to 2. The polynomial will be of degree 2, which is defined as p2x equal to f of x0, first order divided difference for x0 and x1, x minus x0, this factor we write. This is the second order divided difference multiplied with these factors x minus x0, x minus x1. If you look at the diagram, this is the original function, and definitely these are the function values represented by the red dots. Now approximation of this original function, which is p2x. So you can see here this green curve P2x passes through the given data points. Okay, these three data points. So for n equal to 2, Newton's form of interpolating polynomial is a quadratic polynomial. That is polynomial of degree 2. Now we discuss an example. Example is find the Newton's form of interpolating polynomial for the data values. These data values. Here we are given 5 distinct nodes -2, -1, 0, 1 and 2, and corresponding function values are -1, 1, 1, 5 and 19. Since here we have 5 distinct nodes, so the interpolating polynomial will be of degree at most 4, that is P4x. First we construct the divided difference table. In table, this is the first column, 4 nodes, second column for function values. Now we compute the first order divided differences. So 2 is calculated as 1 minus minus 1 divided by -1 minus -2. So these are the first order divided differences. These are the second order divided differences. These are the third order divided differences, and this is the fourth order divided difference, which is 0. After completing the table, we obtain the leading coefficients, means these diagonal values. Okay, so you can see that fourth order divided difference is 0, means the actual polynomial that we will obtain will be of degree 3, not degree 4. Okay, so now we substitute these leading divided differences into this Newton's form of interpolating polynomial. Substituting these values, we get P4x as, you can see here, this -1 value means f of x naught. This is first order divided difference, second order divided difference value, third order divided difference value, leading value, and this is fourth order divided difference value. Okay, since the last coefficient is 0, so final term disappears. Okay, after simplifying this expression, we obtain P4x as x cubed plus 2x square plus x plus 1. So even though we started with the 5 distinct nodes, we obtain interpolating polynomial of degree 3. You can see here a cubic polynomial. So this is very important observation, that the degree of the final polynomial does not depend on the nodes. Okay, so if the higher order divided differences becomes 0, actual degree of the polynomial reduces. This is one of the advantages of the Newton's method, that Newton's method makes it easy to tell the actual degree of the polynomial just by checking the divided difference table. So friends, if you found this lecture helpful, please like the video, subscribe to the channel, share it with your friends, and if you have any doubt or question, write them in the comment section. Thank you very much.